In our final section on the chapter for quadratic functions, we're going to learn how to graph and solve quadratic inequalities and to graph systems of quadratic inequalities. So we've graphed quadratic equations. So what's new is we're going to use the skills we've already learned from graphing quadratic equations and now graph inequalities. And then we're going to graph systems of inequalities. Of course, when you're working with a system of inequalities, I have more than one quadratic function, and I'm looking for the overlapping answer areas when I'm looking at graphing a system. So the key vocabulary here is a quadratic inequality in two variables and a quadratic inequality in one variable. Those are items that may kick up for you on the test. So let's go ahead and move forward. The type of problem that this might be solved for would be to graph the different weights that would be safe to rappel down a cliff using a rope depending on the diameter of the rope. So in this case, they're showing me that a manila rope used for rappelling down a cliff can safely support a weight W in pounds, provided this equation that the weight has to be less than or equal to 1480 times the diameter of the rope squared. Okay, so D is the rope's diameter in inches, and then we want to graph the inequality. Okay, so at the end of this lesson, we'll go ahead and solve this problem by graphing. But for now, we want to talk about how do you graph a quadratic inequality. So first, you go ahead and graph the inequality as if it's an equation. So take the inequality sign, right? Our inequality signs again are less than, greater than, and less than or equal to, greater than or equal to. Remember that if it is less than or greater than, it'll have a dashed line, okay, a dotted line. And what that means is that the line is not part of the solution, the boundary line. When you graph an inequality, you graph a solution area, a boundary line, and a non-solution area. When the line is dashed, it means that the line is not part of the solution area. When we use less than or equal to or greater than or equal to, we use a solid line, and that means that it is part of the solution area. Okay, so that's an important part of your graph. The next step would be to test a point inside the parabola to determine whether the point is a solution of the inequality. Now, in fairness, if you test a point that's inside the parabola, you would want to then relate it to whether or not you shaded inside or outside the parabola, and it should either succeed or fail. So what you might want to do is test a part in the solution area as opposed to inside the parabola. But I will tell you that typically I like to test 0, 0 and just know where it needs to go because it's the simplest item to test. So we'll talk about that when we go ahead and practice this. So what I just said may not make any sense, but I'll show you the different methods of testing once you're in there. And then shade inside the parabola if the step from point 2 is a solution. So here they're saying test the point, and if it is a solution, then you shade inside. If it's not a solution, then you shade outside. I'm going to give you another couple of different ways to do these two steps as we go through. So if I want to graph this particular function, the first thing I want to do is graph the boundary line as if it's an equation, x squared minus 9. So I know that if I want to find the x-coordinate of the vertex, I know it's going to be at 0 because my middle term is 0. 0 over 2 times 1 is equal to 0. And when I go ahead and start making an input-output table, if I plug 0 into this function, I'll get negative 9. So 0, negative 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way down here. I know that's my vertex. If I graph the points 1 and 2 moving across here, I'll have y is equal to 1 squared minus 9, minus 9, which would be equal to negative 8. And y would be equal to 2 squared minus 9, which would be negative 5. So here I'd be at negative 8, and then 1, 2, 3, 4, 5. I know my axis of symmetry is the y-axis, so if I'm one space to the right of the axis, I can go one space to the left and have the same point. 2 spaces to the right, I go 2 spaces to the left. These are my 5 points. And now I want to decide if my line is solid or dotted. Well, this is greater than, so I know it's dotted. It's not or equal to. Or equal to includes the line. So I'm going to do my best here to make a nice, neat dotted line to reflect my graph. Looks something like that. And now I have to decide where to shade. Now what the book suggests is that you test a point inside the parabola, so I could pick 0, 0, that's my favorite point, and plug it in. So y would be 0 when x is 0, right? And is 0 greater than -9? Yes, it is. So I know that inside the parabola is the solution area. This certainly works. What I like to do is I like to go to the y-intercept, wherever it is, or the vertex, actually, wherever it is, and then do this part of it. Y values that are greater than my vertex. Well, greater than would be up. Up leads me inside the parabola, so I would graph inside the parabola. I would shade inside the parabola. There, I made a little bit of a mess, but I'll clean that up here in a second. Inside the parabola. Remember, the dotted line tells me that the area of the line itself is not part of the solution area. Okay? So that's the extra step you've got, is determining whether or not the line is solid or dotted, and then shading either inside or outside the parabola based on some form of a test. Okay, let's go ahead and do another problem. I again want to find my vertex, so I have the opposite of b over 2 times a. So I'll have -9 over -4, -9, so that'll be 9/4. That's not a super fun coordinate, but that's right, it'll give us some practice with fractions. When I plug 9/4 in here, I'll have -2 times 9/4 squared plus 9 times 9/4 minus 4. And when I simplify this, this will become -2 times 81/16 plus 81/4. Now, when I look at this, I know that -2 times 16, I'm going to go ahead and leave this as -4 now. This is -2 over 1. I can cancel the 2 with the 2 and the 16, that leaves 8. So I'll have -81/8. So I know that 8ths are going to be my common denominator. So then this will be 162/8 minus 32/8. So I created common denominators here. -81 plus 162 is 81. 81 minus 32 would be 49. So it's 49/8. That also is not a super fun number, but let's go ahead and graph this. 9/4 is 2 1/4, 1, 2 1/4 approximately. So I know my axis of symmetry comes through here. Okay, then 49/8. Wow, when I think about that, I know that 6/8 is 48/8. So it's just a 1/8 more than 6. So if I come up here 1, 2, 3, 4, 5, 6 1/8, there's my vertex. Okay, now I want to pick 2 points to the right or 2 points to the left of that vertex. I'm going to go ahead and pick 1 and 0, 2 points to the left. Notice that even though I had a fraction for my x-coordinate of the vertex, as I move forward, I'm picking integers to plug in. So when I plug 1 in here, I'll have -2 plus 9 minus 4. -2 plus 9 is 7. 7 minus 4 is 3. And when I plug in 0, I'll get -4. Right? This becomes 0, that becomes 0, and I just get -4. So at 0, I'm at -4. 1, 2, 3, 4. At 1, I'm at 3. 1, 2, 3. And now I want to use symmetry to plot to the other side. Now, I am 1 1/4 away. So if I go 1/4 and another 1 away from the axis of symmetry, that's here at 1, 2, 3.5. And if I go another 1 further than that, I would also be at -4. Now these are the 5 points I'm going to use to graph. I know that y is greater than or equal to, so that's a solid line. So I'm coming through here, doing my best to make a nice smooth solid line. Okay, and now I need to shade inside or outside of the parabola. Now, the book suggests you test a point inside. I'm saying that's too much work. Go to the vertex and do whatever this is. Y values that are greater than. Well, greater than or here is up here. This is outside of the parabola. So I shade outside of the parabola. And this is my solution. Okay, so if you want to test a point inside the parabola, then if it makes a true statement, you shade inside. If it makes an untrue statement, you shade outside. Or you can follow my rule, go to the vertex, and do whatever this says. Y greater than, I would move up. That leads me outside of the parabola. I shade outside of the parabola. Okay, now we're looking at quadratic systems. Now I have 2 quadratic functions that I have to graph. So I'm going to graph them one at a time, and then I'm going to find the area where the shading overlaps. So first I'm going to graph this guy. It's a root form, so I know that the vertex is at 0, 0. I'm going to make an input-output table for this. So I know when x is 1 and x is 2, that's what I'm going to work with. When x is 1, y is -5. And when x is 2, y is -20. Wow, that drops really fast. Okay, so at 1, I'd be at -5. 1, 2, 3, 4, 5. This is great review, by the way, for graphing in general. And 2, I'd be at -20. That'd be way down here. Okay, in fact, because this is really difficult to get on the graph, I'm going to change my scale. I'm going to put down here now that these are 2's. So when I was at 1, I'd be at 2, 4, 5. And at 2, I'll be at -20. And that makes it a little easier to fit it on the graph. I match points on the other side. It's greater than, so it's a not or equal to, which makes it a dotted line. Again, I'm going to do my best to make a nice tidy dotted line. This is super narrow. And then I'm going to go to the vertex and figure out where I shade. Well, I want y values that are greater than, so I shade outside of the parabola. So I'm going to use yellow for this, and I'm going to go ahead and shade the area that is outside the parabola. Okay, all this area out here is part of that solution. Now I'm going to go ahead and graph the other equation, right? Y is equal to 3x squared minus 2. I know that my vertex in this case, right, I have no middle value, so I know I have the opposite of 0 over 2 times a, so that'll be 0. So I'm going to use 0, 1, and 2 again in this equation. When I plug 0 into this function, I get -2, so my vertex is at -2. Remember, I'm going by 2's, so this point here is the vertex. You'll notice this one opened down, but this one's going to open up, so I know it's going to go somewhere around in here. Okay, when I plug 1 in, 1 squared is 1, 1 times 3 is 3, 3 minus 2 is 1. When I plug in 2, 2 squared is 4, times 3 is 12, minus 2 is 10. So at 1, I would be at 1, which would be right here, and I'm matching it to the other side. And at 2, I would be at 10, 2, 4, 6, 8, 10, right here, and I match to the other side. Again, it's a dotted line, so this is going to go this direction. And again, I want y values that are greater than. So greater than here would be up. Oh, that's inside the parabola. So you notice that in the first parabola, up led us outside of it. So I shaded outside. Because this parabola opens up, now when I go up, I'm inside the parabola. So I'm going to shade inside the parabola. And I'm looking for the areas that overlap. So it's all of this area here inside the parabola above this vertex, right? So I'm actually going to go ahead and wipe some of the stuff out of here, right? Because it had to be areas that overlapped, right? So this little piece here, down in here, isn't part of the solution area. It's all this area up above here, above the vertex of the first parabola. Okay, if you want to do it differently, you can do cross-hatching, right? I used colors. This is my solution area here. Right, another example, right? Those others were pretty easy to graph. These are a little more complex. They've got a few more bits and pieces in them. If I want to graph this function here, I want the opposite of 3 over 2 times 3. So this is negative 3 over 6, which would be negative 1/2. That's the x-coordinate of the vertex for this guy. If I want to find the vertex, I'll have 3 times negative 1/2 squared plus 3 times 1/2 minus 5. Negative 1/2 squared is 1/4 times 3 is 3/4. 3 times 1/2 is 3/2. Oh, I'm sorry. This is negative 1/2. My mistake. So this would be minus 3/2. And then minus 5. So I want to create common denominators. I'll have 3/4 minus 6/4 minus 20/4. 3 minus 6 is negative 3. Negative 3 minus 20 equals negative 23/4. That's the coordinate of the vertex. So I'd be at negative 1/2 and, sorry, negative 23/4. I didn't copy that very well. Negative 23/4. So 23/4, that's 5 3/4. So 1, 2, 3, 4, 5 3/4. So right about there. That's my vertex. I'm going to go ahead and I'm going to need more room here. So I'm going to go ahead and do an input-output table. I'm going to use 0 and 1. When I plug 0 in, I'll get negative 5. When I plug 1 in, I'll get 3 plus 3, which is 6, minus 5, which is 1. So at 0, we're at negative 5. That's right here. But at 1, we're at positive 1, all the way up here. So 1/2 away from my axis of symmetry, I was at 5. 1 1/2 away, I was at 1. There's my graph. Y is greater than, right? So it's going to be a dotted line. So I do a dotted line. And I want to know what area to shade. I want to go to the vertex and do greater than. That leads me inside the parabola. So my solution area is inside the parabola. When I graph my second function, I'm going to switch to a different color pen. So I'm going to use a red pen. I hope you don't mind red. So I'm going to have to find the vertex of the opposite of 5 over 2 times a, which is negative 1. So I'll have negative 5 over negative 2. That's going to be 5 halves. So my vertex will be at 5 halves. That's 2 1/2. If I put my axis of symmetry in 1, 2 1/2, right, there's that one. I didn't put the one in here. I probably should have done that. It's right over here. Oops. Let's fix this guy and move him over just a touch. All right, that's better. All right, when I plug 5 halves into my equation, I'll have the opposite of 5 halves squared plus 5 times 5 halves plus 10. And this will be the opposite of 25 fourths, plus 5 times 5, which is 25 halves, but I want it to be fourths, so that's going to be 50 fourths plus 40 fourths. So negative 25 and 50 is 25 fourths plus 40 fourths equals 65 fourths. Right, that's a little bit big, but it's just a little over 16, right? 16 would be 64 fourths, so I need to go 1/4 higher than that. Unfortunately, I was already working in ones, so I don't want to go back and regraph everything. So this is 10, then 11, 12, 13, 14, 15, 16. So we're all the way up here. Okay, and then if we go ahead and create an input-output table, I'm going to use points to the left here, so I'm going to use 2 and 1. And when I plug 2 in, I'll have the opposite of 2 squared, so that'll be negative 4, plus 5 times 2, that's plus 10, plus 10. So negative 4 plus 10 is 6, plus another 10 is 16. So really close here, right about there. And I'll have the same point on the other side. And then when I plug in 1, I'll have the opposite of 1 squared, which is negative 1, plus 5 times 1 is 5, plus 10, so negative 1 plus 5 is 4, plus 10 is 14, so 15, 14, there we go, and over here. Now this is y is less than, so I have a dotted line. I want to go ahead and plot my dotted line. I know that I'm going to have an intercept here. That may help me as well to help get the shape. Right, and we go like this. I want y values that are less than here, so below here is also inside the parabola. Right, and you can see that if I extend this line on up through, the solution area is the area that lies in where the two parabolas, the insides of the two parabolas, overlap. So this is my solution area here. And I've graphed my system. Okay, so now when we talk about solving, we're going to look at solving in a couple of different ways. First thing I would want to do is put this into standard form. So I'll have x squared plus 8x plus 7 is less than or equal to 0. Remember, I'm solving. And if I'm going to make an input-output table here, I might want to consider what's the best way to make an input-output table. So I'm going to do this horizontally. I don't often do it that way. Normally I do it vertically. But one thing that will help me is to get guidance, I might want to know where's the vertex, and I might want to know where the intercepts are. So if I factor this and put it in intercept form, that might be easier. I want factors of 7 that add up to be 8. So that's x plus 7 times x plus 1. Right? And then what I want to do is I want to find these solutions. So negative 7 and negative 1. So I know that when x is negative 7, y is 0. And when x is negative 1, y is 0. Remember, I want values where this product is going to be less than 0, right? This product, it is 0, and at this product, it is 0. So I know that my solutions are either going to be in between these two values or beyond these values. Okay, so let's check some other values. So when I take say -6, what will I get? I can plug it into either one. I might as well plug it into here. -6 plus 7 is 1, and -6 plus 1 is -5. So this would be -5 is less than or equal to 0. Yes, it is. If I do -4, sorry, -5, let's plug -5 in, then I'll have 2 times -4, which is -8, is less than or equal to 0. Yes, it is, -8. Right? Where would my vertex be again? -7 plus -1, right? The x-coordinate of the vertex. It's helpful to me because I know where the lowest value will be in this particular case. -7 plus -1 divided by 2, that's going to be -4. Okay, so that's the next point I'm going to do, -4. Right, remember, we're symmetrical, right? So once I go past the vertex, I really don't have to do other points. I'm going to go ahead and put in -3, -2, -1. Remember, -1 was 0. Right? Because I know if this is the vertex, I know that this value will be the same as the one that's the same distance from the vertex on the other side, and the same for this. So it saves me a lot of work. Right? When I plug in -4, -4 plus 7, sorry, excuse me, -4 plus, when I plug in -4 plus 7 is 3, and -4 plus 1 is -3. That's -9, which is less than 0. And that goes in here. So remembering that, right, my parabola opens up. I know I leave the leading coefficient that's positive. These are the values that will result in y's that are less than or equal to 0. Right? If I go further in this direction, and I can show you, if I use -8, -8 plus 7 is -1, and -8 plus 1 is -7, that equals +7, and that is not less than or equal to 0. So that would not be part of the solution. So all of these guys out here and all these guys out here will not give me values that are less than or equal to 0. So for my solution, I know that my x values, right, this will be expressed as a compound inequality because my x values lie between -7 and -1. So I know that my x values are greater than or equal to -7 and less than or equal to -1. Okay, so this is one way of solving these by using a table. You could see that maybe it would have been easier to solve this by graphing. So if we want to solve by graphing, I want to put it into something like standard form. Subtract 7, we get -9, less than or equal to 0. I look at this and I go, oh, well, I can factor a 3 out of all of this. That's nice. X squared minus 2x minus 3, less than or equal to 0. Now I could graph by finding the vertex, but I also might want to find factors of 3 with a difference of 2 like I did before. It's nice to put it into intercept form because you can find your solutions very quickly. This is x minus 3 times x plus 1. So I know my intercepts are at 3 and -1. Here's -1 and 1, 2, 3. So I know that my solutions are either in between these 2 points, that's possible, or beyond these 2 points. One of the two. Right? When I go ahead and start graphing this, remember this guy's going to open up, so it's going to go in this direction, right? My vertex is halfway between these two. 3 plus -1 divided by 2, the x-coordinate of the vertex. That's going to be 2 over 2, which would be 1. So my axis of symmetry is here at x is equal to 1. Then when I do an input-output table, I'm going to go ahead and do 1 and 2 to find the vertex and a point in between here. When I plug 1 in, 1 minus 3 is negative 2. So I'll have 3 times negative 2. And 1 plus 1 is 2, less than or equal to 0. So 3 times negative 2 times 2, that's negative 4 times 3 is negative 12. And that's certainly less than or equal to 0. So negative 12 would be all the way down here. There's 11, 12. When I plug 2 in, that, by the way, is also my vertex, 1, negative 12. When I plug 2 in, I'll have 3 times 2 minus 3. 2 minus 3 is negative 1, over 2 plus 1, which would be 3. So this would be negative 9, less than 0. Yeah, it certainly is, negative 9. So that's right about here. And then also I can put in the matching point over there. It's or equal to, right, solid line, which also means that those 2 points that are my intercepts are included in the solution. So when you look at this, where are the values less than 0? It's in this area here, right? And what are the x values? They're between this point and that point. So again, it's going to be a compound inequality. I go from negative 1 to 3. So x is greater than or equal to negative 1, and it is less than or equal to 3. And now to solve algebraically, what we're going to do is we're going to treat these like they're equations and find critical values. That's what I did in the last problem actually when I was graphing. I went ahead and found the solutions, which are the x-intercepts. These are the critical values. And they're critical because, as I said when I started, the solution area will either be in between them or beyond them. Okay, so these will be the boundary line between solution area and non-solution area. If we work on treating this like it's an equation, not an inequality, I want factors of 9 that add up to be 10. This would be x plus 9 times x plus 1. I know my critical values are my solutions, right? So now we've called them solutions, we've called them x-intercepts, we've called them roots, we've called them zeros. Now we're calling them critical values, but they're still all the same numbers, right? Negative 9 and negative 1. So what I want to find out is, I have 2 possible solutions. I know that I'm either going to have this solution, a compound inequality, where the values of x that lie between these points, or, right, and now actually or equal to would become important. I put or equal to, but my signs will have to match what's there, right? So that was a mistake on my part, and I'm fixing that. Or it could be that x is less than negative 9 or x greater than negative 1. So here my x values lie in between the two. Here they lie beyond. And how do I know which it is? Well, what I would do is I would test a value between, or I could test a value beyond, but I'm going to test a value between. So when let's say I pick negative 4, that's in between here. Negative 4 plus 9. Negative 4 plus 1, is it less than 0? So negative 4 plus 9 is 5. Negative 4 plus 1 is negative 3. So I'll get negative 15. Is that less than 0? Yes, it is. That means that this is my solution and not this. Why? Because I tested a value that was in this solution area. It was true, so this is the correct answer. Okay, let's take a look at another one. So a little more complicated in my factoring. I know that I don't have a leading coefficient of 1. I know that I'm going to have a plus and a minus in here, and I'm going to have an x there and an x there. The factors of 2 are 2 and 1. The factors of 3 are 3 and 1. And I want products of these factors that will have a difference of 5. Well, 2 times 3 is 6, and 1 times 1 is 1. 6 minus 1 is 5. So that's great. So the bigger factor has to be negative. So I need negative 6 and positive 1. I'll get negative 6 by putting the 3 with the minus, which means the 2 goes over here. Then this is a 1, and that's already a 1. This is my factored value. When I determine my critical values, it's going to be negative 1/2 and positive 3. Sorry, not plus and minus, but positive 3. Those are my critical values. So either I have this solution where x is greater than negative 1/2 but less than, right, and now or equal to, I'm matching that sign, less than or equal to 3. So I'm going to pick a value in here. I'm thinking 0's in there, so that would be good. So if I put 0 in here, I'll have 0 minus 3 less than or equal to 0. Negative 3 less than or equal to 0? Yes, it is. So this again is my solution, right? The other alternative is that if this had failed, I would have had the opposite of this, which would have been x values that were less than or equal to negative 1/2, or x values that were greater than or equal to 3. Because this passed my test, I know that this is not the solution, but it was going to be this one or that one for sure. Okay, now let's go back and solve this problem where we're going to go ahead and graph out this equation. And this equation brings up, inequality, it's not an equation. It brings up some interesting ideas, which I'm not sure we've had a chance to really discuss about, again, the practical nature of examining a real world problem. So I'm going to be working with this function. Again, remembering we're looking for what's the range of weights. How does the amount of weight that a rope can support change as I change the rope's diameter? Logically, it makes sense. As the diameter gets bigger, right? In this case, d approaches infinity. As the diameter of the rope gets larger, my graph is going to do what? The amount of weight that it holds will also approach infinity. So it makes sense that as the rope gets thicker, it can hold more weight. That's all I'm really saying. And also, is it possible for me to have a rope with a negative diameter? Well, no, that's not possible. So I know that this whole area isn't going to be used. This whole area isn't going to be used. I can't support negative weight. So I know that my graph will be completely located here in quadrant 1. Right? That's some basic things that I should understand as I start approaching the problem. So this is a root form equation. I know the vertex is here at 0, 0. Right? I don't have a term with d to the first power, and I don't have a constant. I'm calling them x and y, but what are they really? I've already labeled them. They're d and w. So let me change those to be accurate. It's still an input-output table, and we're still doing it the same way, even though the letters have changed. So if I want to start graphing this, I'm going to look at more of a range. So maybe I'm going to start here at 0, 0, and I'm going to do 2 and maybe 4 as my values, so that I'm looking a little further out to try to get a sense of the shape of this graph. Right? So I know that the weight will be equal to, right, and I'm graphing it like it's an equation, 1480 times 2 squared. Okay, and then that value is going to be 1480 times 4 is equal to 5,920. Wow, that's big. Right? That's a lot of weight. So a 2-inch diameter rope can hold an awful lot of weight. And then if I do this here, obviously it's going to be even bigger. Times 4 squared, 16 times 1480 is really big. It's 23,680. When I look at this, I go, well, that really advanced and got very large very fast. I'm going to do one more point, partly because it's easy and partly to get more detail. When I use 1 squared, it'll just be 1 times 1480. That's going to be 1480. Okay, and you'll notice I haven't really done anything about scale yet. I'm going to go ahead and do these as 1s, right? This is going to be a value of 1. I'm going to do the weight as values of, I think I'm going to do them weight as in thousands. Okay? So diameter is 1, but weight is thousands. That's going to make it easier for me to graph this information. So this is about 1,500. At 2, we're almost at 6,000. 1, 2, 3, 4, 5, 6. So just a teeny bit under 6,000. And at 4, 3, 4, we're way up at 23,000. So this is 10,000. 23,000 would be way up there. So this is the way the graph goes. And then the solution area, I want values of w that are less than or equal to this. So here's my vertex. I'd go down from there. That's outside. But I know, right, it's not accurate for me to shade anything less than 0. So because I knew that everything was going to be in quadrant 1, I'm keeping my graph in quadrant 1. I'll never be able to explain how it is that my rope also holds negative weight. Okay, so this is finding an answer range. Obviously, if I used a 4-inch diameter rope and I only wanted to support 1,000 pounds, it's going to be easy because it can support up to 23,000 pounds. So 23,000 pounds and below. My line was solid because it was or equal to, and this is sort of addressing the problem by graphing.